So today I'm talking about our project to use CVR as a potential biomarker in cognitive impairment and dementia due to small vessel disease. It's an interesting experience that me as a PhD sort of experienced working together with neurologists and clinicians to apply these advanced MR technologies to an interesting clinical question. So Alex asked me to give a bit of educational content. So I will start with some comments about some general discussion. It's obvious that we all know that the Medicare costs in the world are escalating, especially in the US, and people are realizing that. So there are some changes that's going on, at least in the US. For instance, currently, for every procedure a doctor does or every imaging scan that doctor does, we get a fee. It's called a fee for service. But at least in the US, there is a trend of thinking about value-based care. Basically, rather than pay you a certain fee for a particular MRI scan, they will say, okay, we'll give you a certain amount for the entire cost. So the neurologists, the pathologists, they all get combined a sort of fixed amount of payment, and then you divide among yourselves. So that's kind of pose a new question into Medicare and in terms of the expense that we put in as a hospital or healthcare system. So specifically in my home state of Maryland of the United States, Maryland is the only state in the US that started working with the Center for Medicare and Medicaid Service, CMS, to establish a new model, a new payment model, in which in 2014, they started this new model called a global budget model, in which they say that a particular hospital can only receive so much payment of healthcare costs per year. So that means that a big hospital like Johns Hopkins will quickly reach this cap. And once you reach this cap, for any additional MRI scan you do, actually you're only expending more money, hiring tax and paying the service contract, etc. We're not receiving any additional payment. So that makes our hospital has to kind of establish some kind of new strategy to cope with this kind of new system. For instance, our radiology department set up a sort of a spin-off company. They call it JH Imaging, and that's a separate kind of hospital. And then they essentially can receive additional payment without sort of needing to worry about the cap of the Johns Hopkins Hospital itself to receive. So that's kind of the trick that people play to kind of get around this. But this certainly has impact, on our healthcare and practice. And more recently, they started a new model called total cost of care model, in which they say that each person, when they do a hospital visit, they can only receive a fixed amount of payment from Medicare, which means that if a person coming in for, let's say, stroke, if they do CT, then they cannot do a MR, things like that. And the total cost is fixed. So that really asks us to think about sort of what is the role of MR in the medical care business, right? We actually are forced to compete with pathologists who are doing, let's say, these kind of proteomics measurement, metabolic blocks measurement, and also within our radiology, MR compete with PET and CT in terms of like whether this patient should receive this procedure or scan in order to get their disease diagnosed. So this actually is relevant to what we all do, because our goal of doing this research in MR or in imaging physiology is eventually help patients. My dream is to, in the end, have a button on the MR scanner to say, hey, let's measure oxygen ejection fraction, or let's measure CVR, and user can diagnose Alzheimer's disease, stroke, this kind of disease, right? So this is all relevant for practical purposes beyond publishing paper or getting grants. So I sort of want to kind of bring a bit of sense of urgency for the MR community, including the imaging cerebral physiology, but I think it's broader MR community, to say that it used to be that the brain is obvious modality to MRI is an obvious modality to brain disease diagnosis. But actually, when I go to a clinical conference in recent years, there is sort of a change. Let me give you two examples. So yesterday we talked a lot about stroke, but actually, if you go to International Stroke Conference, ISC, or other big conferences of clinical neurologists, you will find that the first modality of imaging for stroke, at least in the hyperacute setting, is CT, not MR, right? Of course, there's many reasons for that, but the fact is that sort of CT is a preferred modality of a brain disease, stroke, which is a very big brain disease. And for the topic of this talk, in terms of dementia, including impairment, if you go to AAIC, which was held, I think, earlier this year in Amsterdam, the biggest conference in Alzheimer's disease, you will find that a few years ago, the biggest topic, the hottest topic in this field is using PET. PET can be used to image amyloid and to image tau. And these are used widely, not necessarily in clinic, but I think getting toward the clinic. It's expensive still, but I think it's sort of the hottest topic in AAIC, those major mainstream neurology conferences on Alzheimer's and dementia. And recently, if you go to AAIC, you'll find the hottest topic is plasma. Plasma meaning you can use blood to measure amyloid content of the brain and use blood to measure tau and p-tau content in the brain. And they are gradually moving to our clinic to be used in routine diagnosis, right? So what is MRI making contribution to these kind of important field? So that's kind of a question we have to face one day. The neurologists will say, why do we need MRI? MRI probably is only useful to rule out some disease, but not really diagnose some disease. And if you look at, continue along this sort of cognitive impairment dementia story, if you look at the mainstream thinking in the Alzheimer's field, Cliff Jack et al. Proposed this so-called pathological cascade of Alzheimer's disease. They think that amyloid beta build up first, and a bit later the tau start to come up, and then they have neurodegeneration shown in the screen, and then clinical manifestations start to come in. So this kind of mainstream thinking also pointing to what measure can be used to kind of determine these biomarkers. And you can say, okay, brain structure, maybe MRI can contribute, but that's like an old school MRI. We can do MP radiology a long time ago, but there are many new studies going on in other things. But so far, the mainstream, for instance, the Alzheimer's community is still looking at brain structure. And along that line, a few years ago, Cliff Jack and colleagues proposed this new classification scheme for Alzheimer's disease. So they are saying that you should not label a patient as Alzheimer's, as dementia, or as MCI, or as other kind of clinical labels, but instead you can classify them based on so-called ATN biomarker classification scheme. When a patient comes into your clinic, you label them as whether you are amyloid positive, whether you are maybe tau negative, maybe you are neurodegeneration positive. And you put this kind of classification scheme to a patient, because that will really help with treatment. For instance, there's recent FDA approved drug to treat amyloid. You have to have amyloid positive biomarkers in order to receive this treatment, in order to get paid by the insurance company for this treatment. So this kind of ATM biomarker-based classification scheme is gradually emerging in the clinical arena. And if you look at this ATN classification scheme, at least at present, well, amyloid MRI really cannot contribute too much. Tau MRI cannot really directly measure it. Neurodegeneration, well, there are some promise. They say neurodegeneration can be measured either by FDG PET or by structural MRI, meaning like hippocampal volume, or by CSF tau, which is sort of fluid based. So again, sort of saying that there's the trend that gradually MRI has been sidelined in, at least for instance, dementia research, at least in Alzheimer's biomarkers. So that's why I sort of want to start with general comment about that we have to think about our work in the as an MR community in the context of the clinical medicine to see what the mainstream neurologists think of MR as a tool. So, but there's also opportunities, because more recent people realize that Alzheimer's disease really is an exception, not a norm. What I mean by that, when people take, for instance, patients are diagnosed with Alzheimer's dementia, then they die, and then they do a brain collection and do a pathological analysis to look at the brain to see what kind of pathological hallmarks these postmodern tissue have. They found that Alzheimer's disease only is a very small fraction of these patients who were labeled as Alzheimer's dementia when they were alive. But in reality, most of the patients actually have mixed dementia. That is, if you look at them, actually maybe more than, let's say, 80% of the patients actually have mixed dementia. obviously, there's AD pathology, but there's also a lot of vascular pathology. So this vascular pathology is not necessarily like large vessel, not stroke or moya kind of large vessel, but they actually small vessel disease due to arterial sclerosis, sometimes cerebral amyloid angiopathy, sometimes microhemorrhage, that kind of small vessel disease. That's why small vessel disease has received a lot of attention in recent years. You heard a few talks yesterday and the day before yesterday on this topic. So people realize that the single pathology such as Alzheimer's is an exception, not a norm. Most people have mixed. So that brings an opportunity, I think, for many of us in the MR field that we can propose to add a V to the ATN classification scheme. Right now, it's amyloid, tau, neurodegeneration. We can add a vascular biomarker to this classification scheme because that can guide the diagnosis of this mixed dementia and certainly treatment option. So, and I think in that regard, my feeling is that MR has a lot to offer. And in fact, I think MR is a leading modality in the biomarker development for the vascular cognitive impairment and dementia. So let's first look at what is the current sort of hallmarks of small vessel disease. Joanna Woodlord had a nice review paper a few years ago. You can see that currently the traditional anatomical MRI can be used to look at recent infarcts, hyperintensity. You heard a lot about this already. Lacunes, this is a dark hole. It's lacune. And the perivascular space, you also heard about, I think yesterday, about the enlarged perivascular space in the small vessel disease patients, and the microbleeds, which sometimes can be caused by cerebral amyloid angiopathy, and recently also by treatment of anti-amyloid immunotherapy. So these are good starting point for MR as a sort of modality to provide a biomarker of small vessel disease. So there's certainly more room for MR to contribute. And obviously, I'm going to propose that physiological biomarker has a lot of potential in this regard. And you know these advantages. So it's easy to interpret. We often can measure something physiological. You know, it's planogram tissue per minute for blood flow, and CMR2 has a nice physiological unit, etc. And they also happen probably earlier, because once you see those lacunes, once you see those perivascular, it's not going to be changed after your therapy. But physiological things we can change. We know we can change blood flow easily. We can change lots of things physiologically quite easily with drug and medication. More modifiable, I sort of talked about it. And the change of size is big. We know blood flow can change easily by 50% if we do something about them. Whereas, brain volume, you really cannot change too much. So I think there's a lot of potential for physiological imaging to play in the VCID field. And so as my title indicated, so my hypothesis is that the CVR can be a potential biomarker in small vessel disease. And the CVR measurement, you all know, I sort of will just go over. So it's, you change CO2 in the lung, which can exchange into the pulmonary circulation, which will be pumped into the heart and then go to the brain. And in normal brain vessel, CO2 will dilate a blood vessel. You use MR as a readout to measure its response. And you can also do, for instance, resting states has fluctuation, as Blaise talked about this yesterday. And I think Molly Bright and Kevin Murphy talked about breath. We also been doing some modulation of breathing patterns. So there's different ways to modulate the CO2. It's not going to have to be CO2 inhalation. Can be other methods. So we became interested in this field of looking at small vessel disease and the CVR as a biomarker, and we have some sort of do some foundation work to make us prepared to get into this field. We first look at the age difference, and we know that as we get older, our small vessel become a bit not as healthy. So indeed, we found that in this lifespan study, we found that CVR, as shown in this red curve, decayed by about 40–50%, comparing 20 years old to 80 years old. Whereas in the same lifespan, the blood flow actually only decreased by about 20%, and that's of course because audio regulation. Because we try our best to maintain the constant blood flow, and in doing that, actually sacrificing the CVR. And we, like others, like Manners and Joe and others, we also did some large vessel disease such as moya, and similar to your findings, we found that CVR is actually an excellent application actually excellent tool for moya. You can see that in this case, the MCA, AC are plotted, and you can see that the corresponding flow territory in those regions are gone. And then with posterior circulation is fine, so therefore CVR and posterior circulation is fine. And when we do CBD as measured by O2 inhalation, they actually are quite normal apparently. We also show that with pre-surgery treatment, pre-surgery, it shows a deficit in CVR, and after bypass surgery, it goes up actually bilateral, even though surgery was done on this side, but actually it improves on both sides. For CBV, doesn't seem to have much change, but actually we found that CBV in baseline actually was a little bit higher than normal. We were also quite interested in normal variations in CVR. In my assessment, I think right now with this kind of 3 Tesla with SMS and with all these high-end MI hardware and software, CVR signal change of 3% is quite stable. It's sort of it's sufficient to get a reliable measure. But the problem, I think, right now, the remaining problem of CVR is that the normal variation is still big. Like if you recruit a group of 20 years old healthy volunteer, the variation in CVR is still quite big. I think that is a normal issue with the current CVR. And we try to do some work trying to understand why there's variation across different people in terms of their CVR. And in this study, we show that the baseline CO2, different people have different baseline CO2, and we found this has an influence on their CO2 CVR values, and try to do some correction, etc., using CO2 as a regressor in our analysis. And yes, as you saw from Daniel's talk, we are also interested to see how caffeine can create normal variation in CVR. If you drink a cup of coffee, then come to the MRI scanner versus not drinking it, it may have a difference in CVR value, which we are trying to understand, and hopefully maybe can find a way to normalize it. All these efforts try to prepare us to use CVR as a biomarker in disease, especially in global disease. I think for the regional ones, such as moya, probably this global variation in CVR is not a big factor, but for a diffuse disease, such small disease, I think normal variation across people is a big factor here. So at the time in 2015, the NIH, the US Congress gave NIH sort of a big bolus of money to start encouraging Alzheimer's research. So they say that from 2015 to 2000, I guess current 2023, the money to research in Alzheimer's has increased by fivefold. That's a big increase. And the US Congress said this is a national plan to address Alzheimer's disease. And they set up a few goals. One of the sort of, to me, the most ambitious goal is to prevent and effectively treat AD and ADRD by 2025. We are in 2023, so we will see whether this plan will materialize. But at least in 2015, that's the motivation to give this big amount of money to encourage people to do Alzheimer's disease. And that's why you see lots of people in the US start to jump into doing dementia research, because the funding is indeed there. So that's also when we sort of start to start looking into small vessel disease, etc., using CVR. And at the time, NIH, the branch called NINDS of NIH, announced a grant opportunity to develop biomarkers for small vessel disease related to VCI, called the MarkVCID study. And and the goal of this sort of study is to establish clinical trial ready biomarker, meaning that you can use the biomarker in clinical trial as endpoint, as patient selection, and sort of to really use in clinical settings. And we applied for this grant and unfortunately got funded. So the MarkVCID study has 3 phases. So one phase is the first phase, is kind of a preliminary phase for 2 years, where each site do their own study. It's a single site study, and each site do their own biomarker. And in our case, of course, we are trying to do a CVR. So we recruited about 28 normal and 44 MCI/dementia patients. And these patients are all sort of enriched for vascular risk factors. So they have a high fraction of hypertension, hypercholesterolemia, diabetes, smoking, BMI, so tend to have a bit more vascular risk factors to ensure that we are really looking at patients who have small vessel disease. So we recruited these participants, and we did CVR on that. In this particular CVR paradigm is we use 50 seconds. So similar to other people, we're trying to reduce the duration of CO2 breathing blocks to sort of ensure that nothing bad is going to happen to our participants. So we only do 50 seconds of CO2 breathing at a time. And in our experience, they couldn't tell that they were breathing CO2 because of such a short breathing block. And we do 3 blocks and do this analysis. And we found the first thing we found is that, sorry, that is the cut slide on the bottom. But the first thing we found that the impaired participant has lower CVR compared to normal participants. We tried this in different regions, different lobes. We found that they all show similar things. There's not much regional dependence, so it's global CVR that we've used as the biomarker. So we found that it's lower in impaired. So next we look at the relationship with CVR and cognition, because that's in the end, that's what matters in terms of cognition. So we found that the global CVR is nicely correlated to MoCA, which is Montreal Cognitive Assessment. It's an index, it's a 30-point index of global cognition of the patient, of the participant. This takes about like 20 minutes to acquire. We also doing a 2-hour more comprehensive cognitive assessment using sort of different tests. Different tests are combined into different domains of cognition, and the domains is combined in turn to become a composite cognitive score. And we found CVR is also correlated with this global composite cognitive score. So this is all good. But just by comparison, we looked at the basal CBF measured, by ASO, or, similar technique like that, and we found that in global whole brain CBF, it was not so much correlated with MoCA, as you can see on the right-hand plot. We talk about mixed dementia, so we have to consider this CVR in the context of Alzheimer's pathology. And here, Alzheimer's pathology was measured by cerebrospinal fluid sampling and measured from the CSF, their amyloid and tau levels. We indeed found that both CVR and A-beta are simultaneously associated with MoCA and with the composite score, meaning that so the variation in your patient's cognition can be partly explained by CVR and partly explained by beta amyloid. Again, indicating that it's the mixed pathology, mixed sort of 2 hits that cause this cognitive decline and dementia eventually. And it's important to know both pathology, both the A-beta and vascular pathology in these patients. So again, highlighting the importance that CVR can play in parallel with amyloid beta. We also look at specific cognitive domains. We found that the most domain that's correlated with CVR are language and processing speed, and these are sort of classic conditions, classic symptoms that a vascular dementia patient would have, as opposed to memory, for instance. In the US, there's a big emphasis on reproducibility, on the repeatability of a finding of observation. So we also want to show that the CVR is reproducible. This is reproducible finding. So that in the same patient, same sort of dementia and the impaired patient, we also did phase conscious-based CVR, and the phase conscious used blood flow across, let's say, in the sagittal sinus to measure the velocity and measure the flux, essentially the blood flow in this vein. And we can see that whether this increase with hypercapnia, and that's also an index of a CVR. We call it CVF-based CVR because it's better than both, because we know both the signal is complex with lots of components, whereas CVF-based CVR we think is somewhat cleaner. So you can do phase conscious during room air and during hypercapnia. You can see signal become brighter because blood flow has become higher, and therefore you can use the difference to calculate phase conscious or CVF-based CVR. And we happily found that this finding is similar to the bold case, where MCI in dementia patient has lower CVF-CVR compared to the normal controls, and the CVF-CVR is also correlated with MoCA, just like the bold CVR. You can see that, by the way, you can see that the value of CVR-based CVR is on the order of 4 to 5. That is 4 to 5% change per millimeter mercury CO2 increase, different from bold. Bold typically is on the order of 0.15, 0.2. But this is essentially because of different measures. But this does show that this kind of relationship between CVR and cognition is reproducible because phase conscious measurement is an independent measure from bold. It's sort of just it's an independent verification. And the CVR measured by CVF actually is also correlated with their physical function as measured by gait speed and sort of 5 hair spans. And it's also related to the severity of dementia as measured by global CVR, clinical dementia rating. And we also found that CVR was related to HbA1c, so perhaps indicate that diabetes is a major sort of component, major factor in driving CVR related to small vessel disease. So I would say, when you design future CVR experiment, keep an idea, keep a MRI in mind. Maybe that's a alternative way to acquire CVR in addition to your board. And so the PC-CVR is reliable. It only takes 3 minutes. In our case, we do 1 minute of room air, the blood flow measurement, and then switch to the CO2, and we wait for 1 minute, and then do another 1 minute of hypercapnic CDF measurement. So like 3 minutes as opposed to 7 minutes. So it's also a little shorter. The only downside is that it only provided global measurement, but without regional information. But for diffuse disease, maybe it's okay. And it's, of course, CBF is more quantifiable, more quantitative. So we did a study, and at the phase 1 study, so the NIH made a competition. So each of the sites proposed some biomarkers they tested on individual sites, and they select which ones they want to advance to next phase based on the data we present. And we were lucky that CVR was selected as one of 11 biomarkers, maybe move on to phase 2 of the study. So then we went to phase 2, which is from 2018 to 2022. So in this case, they have a bit higher standard. So each biomarker has to be into a kit. So have to be scalable in other places. Okay. That's important for us because we can do CVR in our own institution, but when you go to a neurology clinic, you ask them to do CVR, they get scared. And when I went to one of the first meetings of the consortium, they say, you want to do what to my patient? I want to inhale carbon dioxide. So, there's some resistance. So we have to kind of, and they, of course, don't know how to do it. So we have to kind of, overcome this obstacle. And also want to standardize acquisition and data processing. Of course, everything has to be standardized, have it doable on every scanner at every site. And they want multi-site. They essentially want observation to be reproduced at different sites, not just one site. So they want to avoid sort of this random chance. And another thing they require, the statistical analysis has to be predefined. You can't just, let's acquire data and try different ways. Frontal doesn't work. Let's try parietal lobe, or let's try temporal. They want you to predefine. They want you to put all the eggs in one basket before you even start acquiring data. So this is a lot of requirement. And then data from each site need to be confirmed the predefined hypothesis, meaning that when you do analysis, you cannot aggregate all the data from all sites. You have to try the analysis on each site, and each site has to produce the same finding that predefined. It's pretty high bar. So, but that's what we got into ourselves into. So then we sort of try to modularize our experiment. So we tell every site we'll ship you a box. Ignore the Sam Phillips. This is not a promotion for Phillips. We just happen to use a box. But we put together this kind of 1.5 feet by 1.5 box. We ship to every site. In the box has everything that's needed to do the CVR experiment, including CO2 monitor, the valve, and the pipe, the tube, and everything. It costs about $4,000, which we think is reasonable. Considering we're talking value-based medicine now, so we think it's reasonable. And then after they receive it, they have to order their tank. We cannot ship the tank to them. They have to order their CO2 tank. But everything else is inside this box. And once they receive this box, me and a few colleagues of my group, we travel to different places. This is in Houston. This is in Jacksonville Mayo Clinic. This is in UC Davis. So I got lots of mileages out of this project. I'm a gold member of United Airlines, so that's the benefit of it. So that's sort of, make other sites are able to do CVR, but they also have to kind of show that it's reproducible. So we did a few studies to do that. Firstly, we did at our own site where we bring 10 healthy subjects. We bring them in for a CVR on scanner 1 of one vendor, and then take a short break and do a CVR again on the same scanner. Then move them to another scanner of another vendor. We did another CVR and break. And so this allows us to look at the intra-session, intra-scanner kind of variabilities. In general, we found that this is actually a Siemens and Philips scanner. They show pretty good correlation in young controls, and there's no clear bias as shown by a blind Altman plot. And image-wise, they all show pretty decent image quality. So show that this thing can be done on different scanners. Different scan does not produce a systematic bias on the CVR results. This is important for multi-site because different sites have different vendors of scanners. The next thing we did in reproducibility is that we show that people who are new in CVR procedure can also collect data reliably. So we ask each site to collect a few people, and each patient actually come in on 2 different days. So that can also account for inter-day variation in CVR. And then we sort of compare their reproducibility. Now, there's more variation, but in general, there's still a significant correlation between day 1 and day 2. So this also includes day-to-day variations. So in general, I think there's a correlation, and there's no obvious bias between different scans. Generally show that it's doable and it's generally repeatable. And we also want to standardize the processing. So what we did is that we developed this cloud-based CVR processing, in which essentially a user only needs to upload their bowel data along with the CO2 recording data, and then click submit button on a particular website shown here. And then you wait for 20 minutes or so. And once the data is processed, the results are available for download, you can click the button to download results, and then you will receive a zip folder. If you unzip that zip folder, there's a bunch of files. And these files include, for instance, absolute CVR maps and relative CVR maps after scaling by global CVR. And this map has been transformed into empiric space, standard MNI space, as well in the individual board space. And this is done by voxel-wise as well as global shifts. We also provide a region of interest results. We divided the brain into different levels, up to 289 brain structures, and sometimes 50 structures, different levels of postulation. And for each region, you have a CVR value as well as a quality interest indicator, which is essentially the cross correlation coefficient between the bowel time course and the CO2 time course. And we also provided the basal and the maximum CO2 change. So kind of this tool we developed as part of this project. And so then we can collect data, and we collect this data. So we pre-specify a site has to have at least 75 patients in order to be considered to have enough sample size, enough power to do this analysis. We pre-define that as well. And we put all of our eggs in one basket, which we call global CVR versus MoCA. That's what we are betting. So fortunately, it turned out to be fine. So at all sites, we were able to reproduce this finding of correlation between CVR and the MoCA at every site. Everything, not combined. Combined, of course, highly significant, but each site is also significant. So this is a promising finding, and we present this, at the end of phase 2. So then at the end of phase 2, the NIH made us again, have to select which biomarker to move on to phase 3, and they select 5 out of the 11 biomarkers, and we were lucky that CVR was again selected to be moving on to phase 3 of this project. And we also published a sort of consensus imaging protocol paper in Alzheimer's and dementia. So here is a biomarker that's been selected, the 5-1. You can see that one is called MRI arteriolosclerosis. Essentially, it's a machine learning method to use diffusion and flare to come up with the index. Then CVR is what I lead. There's MRI free water. There is a peak skeleton time mean diffusivity, something that Stanley Fan presented yesterday. So you can see that a lot of diffusion scans, but fortunately we have one physiological marker also being considered as a CVR and also being considered. And there's also biofluid marker, so-called NFL, neurofilament light, which is actually a neurodegeneration marker, also observed in Alzheimer's, Parkinson's, multiple sclerosis. It's not very specific, but it's made to the final list. Just to kind of briefly say, okay, diffusion is still a very big modality because it provides more reliable sort of structural measures than empiric or flare. So you can see that this is what Stanley presented yesterday about PSM peak skeletonized peak width of skeletonized mean diffusivity. Very useful work from Marco During, etc. And this is something that Charlie DiCarli is working on, free water. Then you add an isotropic component to your diffusion model. You measure the free water, and this F index actually is quite useful apparently in small vessel disease. So now we are currently in the phase 3 of the MarkVCID study, which it's actually just started. It's going to continue until 2027 at least. And we are aiming to enroll 1,800 older participants across the 16 sites in the US. and each site is going to do CVR and diffusion and everything. And so the study design that we are going to do baseline evaluation, then follow them every 12 months for 3 time points. And the goal is to ask 2 questions. One, can biomarker, such as CVR or diffusion, predict future decline in cognition? 2, whether change in biomarker can measure change in cognition earlier, rather than waiting for 3 years to see a change, can you find it within 12 months? And that helps clinical trials. And the benefit of this kind of biomarker, according to FDA guideline, is that first, it can use for subject selection. For instance, you can say that, we can do a CVR for all the participants that we potentially can enroll, and only enroll those who have low CVR into a clinical trial of a drug. Second, study outcome. That is, rather than wait for 3 years of treatment of this drug to see whether the cognition improves or stabilizes, we can use CVR to see whether the trial is successful or not successful. So this is the long-term goal of using biomarker in the context of clinical trials. This is the study design. It's too complicated, but then I want to emphasize that we are trying to enroll people who have either diabetes or hypertension, or have one-man hypertension of Likert score bigger than 2, or at least 1 microbleeds, or at least 1 lacunar infarct. We're trying to enroll people who have high risk for small vessel disease. If you have normal cognition and none of these vascular factors, you cannot be enrolled into our study. So that's sort of the design of the general study. It's kind of interesting experience for myself. The Corning Center, the MGH, keep us on a very tight leash. So every month they send out this newsletter to kind of stimulate everyone, saying, "Hey, we are targeting is enrolling 40 patients. Now we are at 1261." And they also make up this small challenge, say, "Hey, this currently Rush and the JHU and UMD are neck and neck at the top recruitment side. Keep us on a very tight leash to have us compete against different sites." And they also show up this table. This sample was sent out to every person in the consortium, like hundreds of people. They say, "Hey, right now you are at 176 or whatever. And if you enroll, enroll a lot of patients in the past 2 weeks, they give you a little running man. So hey, you are the running man in the past 2 weeks." So they really keep us sort of on a tight leash, which is interesting experience. But this is what Steve Greenberg, our Corning Center director, always remind us. Okay, you are here. Keep going. Don't let the gas pedal. Don't lose the gas pedal. Keep going. You are here. We're actually trying to finish the baseline enrollment, and then in the next few years, we are going to do follow-up of this. So retention will be a major question in the next 3 years. We're almost finishing enrollment of the initial cohort. So my take-home message. So I hope I've shown that physiological MRI such as CVR has a role to play in small vessel disease-related vascular impairment and dementia. I think that's an open field that haven't been sort of dominated by PET or plasma or biofluid biomarkers. I think CVR MRI in general has a pretty good role to play. CVR, we show that CVR is related to cognition independent of Alzheimer's pathology. This is important because other people say, "How do we know you are just doing another measurement of Alzheimer's pathology?" We say, "We're not." I mean, CVR also can parallel predict part of the variance in cognition in our participants. And so my general feeling is that right now, the challenge of CVR is still low SNR and large normal variations, which is sort of a problem compared to some of the more structural-based measures such as diffusion. As you can tell, like 3 of the biomarkers that's currently being tested are still diffusion-based biomarker, whereas CVR is the only sort of physiological or functional marker being tested. People have proposed resonance connectivity or based on CVF in the consortium. Actually, they just did not advance to this stage. So it's diffusion structure still has some advantage because they are stable, they are more sort of high SNR. So I think we still have to work on improving the SNR and reduce normal variation if you want to have our biomarker advance to the real clinical arena. I want to thank people, my current lab member and former lab member for their sort of really they did all the hard work. And also, I want to acknowledge the MarkVCID Consortium led by Steve Greenberg at MGH, who is a neurologist leading sort of this big Consortium, having every site do what they are supposed to do. And the external advisory committee, especially Gertian and Bezos, who's actually local professor at Utrecht, who's on the external advisory committee. And with that, thank you very much for your attention.